12:10. Okay. Okay, that's working. Volume. Okay, we just have to. Okay, that's good. The wireless microphone is dead, and I can't figure out how to open the battery case. All right, so what I'm going to talk about today is angular momentum. Tomorrow is energy equation. And so I think I already have threatened you that in this course you're going to spend the most time you ever will on garden sprinklers. And that's because of angular momentum. So we will talk about lawn sprinklers maybe once. I'm going to try another problem than the one I did yesterday for section 2. Just a really quick sort of business thing. I am trying to do the annotations, but I don't want to keep uploading things. So I'm going to try and do it once a week. So once the files are ready for the week, I just put it up once and not have to do it 6 times. Okay. And if you have been very energetic and looking at the notes that I've been posting, you'll notice that yesterday and the day before I probably posted about 4 or 5 different versions. I'm just trying to figure out how to present things in the best way possible. So you continue to focus on control volumes, and now we're going to start to look at the angular momentum vector h. And h is just going to be r cross v, and typically with something like this, we have a fluid coming in and a fluid sort of rotating around, and there's a vector associated with it, and we'll have some sort of m dot v that we have, and r is going to be defined like this. So you want to sort of do the same thing as before. Remember that in the first lecture, or the Tuesday lecture, we did talk about extrinsic and intrinsic properties, and beta is just b divided by m. So it's that table there with all of the information that you need. Time rate of change, just like you did in dynamics, is going to be sum of moments, and it's r cross with f. And so as you solve these problems, you're looking for what the forces are and how to solve through for them. We end up with a general equation, and that general equation, interesting. That general equation is going to take the form, sum of moments are going to be whatever we're trying to store in terms of angular momentum. This is, again, angular momentum only, plus the amount of angular momentum entering and exiting the system. So again, typically, you're going to define control volumes, and when you do that definition, you'll have material entering and exiting, and you might be storing some. Typically in mechanical engineering, we don't store material. So we're not going to deal too much with the first term that I have in the red bracket. The second term simplifies because often we're dealing with 1D flows. And so with 1D, it's r cross with v out, m dot out, r cross with v in, m dot in. And again, the m dot term in both cases are going to be the same because we assume whatever's entering is exiting. So what I want to do is a few examples on this to sort of lay this out a bit. And the first one is a torque problem. I have a pipe bend that is supported at point A. Find an expression for the required support torque TA, then compute it for the given flow conditions, and I'll give you those flow conditions. You have pressure which is acting on both sides, P1, P2. You have V1 and V2 that's exiting. Outer, the atmospheric pressure is gauge pressure, and the density is constant. This is not a compressible flow. The flow is just moving through and coming out the other end. And what I will do is also define, actually I'm not going to do that. I'm going to define a really simple one. So a control volume that kind of looks like this, that covers everything. Now the important thing with control volumes, and this is something that you should practice, it's like your free body diagrams in first year, you need to sort of have it so that the face here is always acting normal to the flow. And then everything becomes a lot easier. If you have a non-normal face, then you're going to have all sorts of flipping around that you have to do in terms of the geometry. So I'm just going to draw a very poor schematic of this. And I'll call that, I have 1, I have 2, I have A, I have H2, and H1. So I have all of the terms that are sort of there. The inlet to this system, I'm going to reference and the exit to the system is 2. I have the point of interest, which is going to be A, so I'm referencing everything with respect to A, and now I can sort of start to look at the problem and solve for things. So it's going to be steady flow, and I want to do sum of moments about A, and that's going to be equal to R cross B out M dot yes, not right now. Okay, something's gone wrong. Ugh. Let me just try something. Oh, there, okay. Sorry. Oh, what is going on? Okay. Sorry. Calligraphy. I don't know what's happening here. Okay, why is it doing that? Okay, all right, well, there we go. Sorry. Okay, if you beat the computer enough, it actually starts to work. So you have all of the material that's going out and all of the material that's coming in. So R cross with V in, M dot in. And God, that's one of the nicest curves I've ever drawn. I have R cross V, and those are, of course, vectors. And I also know maybe it's where my hand was. R cross V, so I have vector terms. I also know that direction is going to be very important in this. And as I go through this, I have to worry about direction. So moments. This is not going to work today. Sorry. I'm just surprised. This is. All right, I don't know what's going on. Hold on. I'm going to switch to another thing. What's going on? Okay, tell me it's not a Windows update. I have no idea what's happening. Okay. Okay. All right, I'm going to try and reboot this machine. Is it work? No, it's not logging me in. Okay, so I'm going to be talking, might as well do it this way. It's not the way I wanted to do it. All right. So, So if you have the fluid coming in, the fluid coming out, the main thing that you worry about is you have a resisting torque which we're solving for, which is TA. We have a resisting moment from the pressure forces and we have a moment from the pressure forces. So if we have a moment from the pressure forces, we have to consider this moment and this moment, because what we're looking at is P2 on this side, P1 on that side, and everything is being torqued there. So that's H1, and that's H2. So total torque is going to be TA plus R1 crossed with P1 A1 N1. Where the normal force is going to be, the normal force, or the pressure force is going to be considered on that. I want to make that negative, plus R2 crossed with negative P2 A2 N2. Which equals R1 or R2 crossed with V2 M dot minus R1 crossed with V1 M dot. All right, so I have a moment that's being caused by the pressures acting on the face, both faces, so position 1, position 2, these right here. I have the restraining torque.
Yes. So I'm confused, why do you have a negative sign?
Because it's always acting in a negative sense. The normal force, if I were, I kind of regret the way I'm doing this problem, but normally what I would do, here I'm if I said, look, R1, which is in the J direction, cross with P1A1I, and then R2J cross with negative P2A2 negative I, if I have it there. And that would make it sort of a little bit better in terms of solving this, but I'm not going to do it that way. I'm going to treat it as a multiplication. So in the next step, I'm actually going to switch the signs. So this is not magnitude, this is a vector equation, and this is how you approach it if you applied it as a vector approach. So, if you do that, you have, again, A, 2, and 1, and you have P1, A1 on the left, P2, A2 on the right, and that's X and Y, and you have a positive direction for the moment that is counterclockwise. So if you do that, and you look at point A, P1, A1, H1 is causing a positive moment. So again, not an ideal way to present this problem, but I probably should have not done it as magnitude. P2, A2 is causing a clockwise moment. And so as it causes that clockwise moment, it goes negative. Then I have the other two terms, which are the out and the in. And that's my solution, or that's my general equation for the torque. So if I look at the other stuff, and sorry, this is slide 160. So that bit was 159, this is 160. These are the values so I'm going to use. So I'm going to substitute things in and solve through for them. My cross-sectional areas, A1, A2 are the same, D1, D2 are the same, and so it ends up being 0.0044 centimeters squared. Velocity is 13 meters per second, so mass flow rate, rho A1, B1, is going to be 57.4 kilos per second. So I can take this equation and go to slide 162. H2 and rewrite my torque expression in terms of the knowns and the unknowns with all the knowns on the right-hand side. So torque is H2 P2 A2 plus M dot V2 minus H1 P1 A1 plus M dot V1. So that's just bringing terms from the right, or left-hand side to the right-hand side, and those terms are the pressure terms. So this term is 25 centimeters, 550 kilopascals times 0.0044 meters squared plus 57.4 kilos per second times 13 meters per second. And that will equal 794.11 Newton meters. I can do the same thing with the other term. Sorry, I'm just going to try again just to see if this thing will even work. Yeah. 5 centimeters, 700 kilopascals, 0.0044 meters squared, plus 746 Newton. And that will equal 192 Newton meters. So the torque A is out minus in, and that will end up being about 602 Newton meters. I think I flipped a sign. Okay, any questions? I saw you first.
I'll go second.
Yeah, perfect.
Did you get V2 by just doing the conservation of mass?
Yeah, so V2 I knew is the same as V1. So the cross-sectional area of the pipe coming in is the same as the outgoing, and so that's a constant value.
When you started writing the moments for pressure forces, you had R1 cross, is that rho A1 and normal vector, or is that pressure times A1 times the normal vector?
Hold on, let me just see. Hold on. When I wrote everything out for the pressure forces, I had R1 oh, maybe it'll work. Okay. All right, so when I wrote out everything for the pressure, I had it written up there as P1, A1, H1. I think before that, I had an R term in there. R1, R is the radial distance between the pressure force that's causing the moment arm. And so that force is really force 2, force 1, and H1. And I shouldn't write it that as a vector because it kind of confuses the situation. It is R cross with MV, or R cross with the pressure, but the R in this particular case is just H, and I'm doing the sort of positioning by inspection.
Okay, so it's all pressure.
It,
The whole problem, right?
no, sorry, so, up there. So at the very top, you see what the whole thing is. So the terms on the left are all of the pressure forces. The terms on the right are all of the momentum forces. So on the left-hand side, I have the restraining torque, which I'm solving for.
Yes.
And this is probably the better equation to work from.
So is that pressure, that's pressure, right? At the top, pressure times area times
Yes, and so, sorry, yes, I hate writing rho and I hate writing P. Both of those, so it's TA plus PA, A1, H1 minus P2, A2, H2. In M dot, it would be rho V times the cross-sectional area. Now, in both of these cases, M dot 1 and M dot 2 are the same.
Yes.
Yep.
Thank you.
All right, and we're going to try again. Now, in the other section, I did do the other examples. I would like to do this example, which is the center pressure. And I think I have enough time if I do it now. If I have extra time, I will also do another example from this. But we'll see. And the first thing is to check there. See, my screen's working. Compute the location of the center of pressure. Okay. Up. L of the normal force. The center of pressure is the point where no external moment is needed to hold the plate in place. And express the result in terms of the initial jet thickness, which is H1, and you have V and V. And in this particular case, V's are again the same. We're going to play games where often we'll have situations like this where we say, okay, this cross-section is the same as that cross-section. And I'll talk more about that in a minute. But my control volume is going to follow along like this. And again, what I'm trying to do is that as the fluid enters the system, it's entering normal to the control surface, and as it exits the system, it's exiting normal to the control surface. Oh, that's not what I want. Sorry. So I have some moments which are going to be, again, R cross MV out, R cross MV in. R cross MV out is positive, R cross MV out or in is negative. The total external moment, the one that is acting to sort of or allow me to calculate the center pressure, is going to be the sum of moments. The right-hand side, the net rate of angular momentum flying out of the control volume. So this sum of moments about O is just going to be minus force normal times L. And again, counterclockwise is treated as positive. So sum of moments about O, you've got a normal force acting on this, acting over a moment arm of the L, and that's going to be what I'm looking for here. So if you look at the control volume, I'm going to define O as some point here, but the jet that is incoming on it is acting at 0 moment arm away from point O. So R is equal to 0 in that case. So it's just hitting that center, and if it's hitting the center, it can't cause moment.
I just wanted to ask, is the moment positive or negative? Isn't it going anti-clockwise?
It's going to resist.
Oh, okay.
So that's, and again, it's one of the problems with looking at drawings of these things, because every time you look at a drawing, you do it intuitively. So we're opposing the motion. So this is one. So when you look at that, you then have the moments that are caused by the linear momentum with respect to point O. And jet 3 is oriented so it will give jet 2 will give a counterclockwise moment, and jet 3 will give a clockwise moment. So you have a net flux on the right-hand side of your equation, and you can say that the forces I wonder. Force normal times L is equal to, or I could, 1/2 V m dot 2 H2 minus m dot 3 H3. So if you go through the algebra, you can start to separate out terms. You can say, okay, look, we have the density of the fluid, which is rho, and instead of writing m dot, we write it as, just one second.
No worries.
Instead of writing it as m dot, we're going to write it as m rho vh, and essentially assume unit depth into the screen. So we then have rho vh2 times h2, rho vh3 times h3, spill all the terms around a little bit, and you end up, and it's h over 2 here, h over 2 at the very top, so the 1/2 comes out, 1/2 rho v squared, h2 squared minus h3 squared. Go ahead.
Could you quickly just go over how you find the directions for 2 and 3? Because it depends on like where you take the arms. Are we looking kind of beyond point O and how that creates a moment of logic? Or like, because 2's pointing up, right? So then when you take the...
So the problem is always that it's the counter moment.
Oh,
So for moving things around, this is where it gets a little bit dicey. So the moments that I expect to come out of this are that. And so when you put all of the terms in there, you end up with these expressions. It's not a great problem. I probably shouldn't do this one. Sorry, go ahead.
oh, I'm just thinking to myself, thank you.
Yeah. So if you look at okay. If you continue, so Fn L is going to equal Fnl equals n 1/2 rho q v sine theta, which equals rho v h1 v sine of theta rho v squared h1 sine of theta. So in terms of the normal force, it's going to be acting against an angle. And because it's acting against an angle, it's going to cause, only a component of it will cause a moment normal to the surface. And that surface angle is going to be rho qv sine theta. So if you have that and you have the other term, you can say Fnl is equal to 1/2 v rho v h2 minus rho v h3 which equals 1/2 rho v squared h2 squared h3 squared. So continuing, L will equal 1/2 rho v squared h2 squared h3 squared all over rho v squared h1 sine of theta. And L will then equal h2 squared minus h3 squared over 2h1 sine of theta. And I'm actually going to leave it in that form right now. And the reason I'm leaving it in that form is you can use a number of geometric relationships and extract out the one that I have at the very top or in the middle of 1/2 h1 cotangent of theta. And basically, it's using the fact that h2 squared minus h3 squared is equal to h2 plus h3 h2 minus h. H3. And then substituting a whole bunch of relationships for cotangent and then simplifying the expression. This is not something that we would expect you to do, and I probably will try and just sort of slap in that particular slide later to get the result, or show you how to get the result. But I don't really want to do it right now. Go ahead.
So, why is Q equals to V dash?
Oh, Q is the area flow rate. And the area in this particular case is assumed to be unit depth, so it's a rectangle of dimensions h1 by 1. And Q or h2 by 1. Both of them are the same. Do you have a question? Any other questions on this one? I may just give you the actual solution that I have here and make my life easier. Go ahead.
So when we're doing angular momentum problems, we're considering, like, R is a vector and V is a vector, right? So like in general, like when we're just, especially with like fluid flows in and out of a system, even though these fluid flows are at an angle, we just neglect that because we're just looking at like the sum of the fluid, or we're not looking
Okay,
at force balance, right?
yeah, so the better answer to your question, and I think in fairness to all, is that I would not do it this way by visualization. I would just write down h1 in this particular case. So when I was solving this particular problem, I would say, okay, that's h1, that's h2, and h3, and I'm doing a moment about this point, and I would say that that is a j direction and a j direction. And I would solve the vector equation. I would not try and do the visualization, because I think the visualization ends up messing you up. And it's not, generally dealing with vector type approaches, it's often preferable to say, hey, just write it out in terms of terms like that. And I'll probably try, if I get a chance, to actually solve it that way.
So just write out all the terms, not back, and it'll come up, like one of them will not be 0, and then that will come into the equation, right? That just might be.
Yeah, one
usually
component,
usually.
that's right, you're right.
Okay, because like, yeah, I was getting confused because like Fn is in the normal direction, then when you project V into the normal direction, it would be 0, so that's why
Yeah.
I was confused.
Yeah, but so Fn is, Fn is going to be is a moment. So I'm assuming that it's acting at a distance L away. So I just called it Fn times L. If I did it another way, a better way may have been to say, I have a restraining moment at O, and I'm going to call it sum of moments